The formation of elements, tracing the origin of chemical building blocks. Title: The formation of elements, tracing the origin of chemical building blocks. Introduction. The study of the formation of elements is a fascinating field that delves into the origins of the chemical building blocks of our universe. From the vast expanse of space to the intricate processes within stars, scientists have made remarkable strides in understanding how the elements that make up our world came to be. In this article, we will explore the fascinating journey of element formation and unravel the mysteries behind their origin. 1. The Big Bang and the Cosmic Abundance. The story begins with the Big Bang, the event that gave birth to our universe. In the early moments of the Big Bang, only fundamental particles like protons, neutrons, and electrons existed. As the universe expanded and cooled down, these elementary particles started to combine, forming the first nuclei, primarily hydrogen and helium. These two elements are still the most abundant in the universe today, with hydrogen accounting for about 75% of its composition and helium close to 25%. 2. Stellar nucleosynthesis. While the Big Bang accounts for the creation of the lightest elements, the birth of heavier elements is a result of stellar nucleosynthesis. Stars act as colossal nuclear reactors, where immense pressure and temperature inside their cores enable nuclear fusion to occur. Fusion reactions involve light atomic nuclei combining to form heavier elements, releasing vast amounts of energy in the process. Most stars, like our Sun, undergo a process known as hydrogen burning. Here, hydrogen nuclei fuse together to create helium, releasing energy that powers the star. This hydrogen burning phase continues for millions to billions of years until hydrogen is mostly exhausted in the star's core. 3. The life cycle of stars. Once hydrogen is depleted, stars undergo a series of transformative stages. In stars with lower masses, like our Sun, the subsequent phase is helium burning. Here, helium nuclei combine to form heavier elements such as carbon and oxygen. As the star ages, it expands into a red giant, releasing elements it has created back into space through stellar winds or explosive events known as supernovae. Massive stars, on the other hand, have a more dramatic fate. They burn through their nuclear fuel at a much faster rate and eventually become supernovae. The explosion is a cataclysmic event that distributes an array of heavier elements forged in the star's core throughout the surrounding space. This cosmic spectacle is responsible for the creation of elements beyond carbon and oxygen, such as iron, uranium, and gold. 4. The crucial role of supernovae. Supernovae play a vital role in enriching the interstellar medium with heavy elements. As a supernova occurs, its tremendous energy and shockwaves propel these newly synthesized elements into the cosmos. 5. Stellar recycling and planetary formation. As the universe ages, regions enriched by multiple generations of stars gradually accumulate higher concentrations of heavier elements. These enriched regions become the stellar nurseries where new stars and planets form. Stellar remnants, such as white dwarfs and neutron stars, can also go through violent processes like collisions or mergers, leading to the ejection of even more heavy elements into space. In these enriched environments, protoplanetary disks form around young stars, composed of gas and dust. Within these disks, gravity causes the dust particles to collide and stick together, forming planetesimals, which eventually evolve into planets. The composition of these planets, including the elements they contain, is greatly influenced by the chemical makeup inherited from the stellar nurseries of their parent stars. Tracing the origin of chemical building blocks, the formation of elements Part 2. 6. The role of neutron capture. While stellar nucleosynthesis plays a crucial role in element formation, it is not the sole process responsible for creating all elements. Neutron capture, specifically the rapid and slow processes, contributes significantly to the synthesis of heavy elements beyond iron. In the rapid neutron capture process, or R process, heavy elements are formed during supernova explosions. During these explosive events, enormous amounts of neutrons are available, allowing atomic nuclei to rapidly capture them and form heavier elements in a matter of seconds or minutes. This process is responsible for the creation of elements such as gold, platinum, and uranium. On the other hand, the slow neutron capture process, or S process, occurs in the later stages of a star's life, particularly during the asymptotic giant branch phase. Here, neutrons are captured at a slower rate, allowing more stable elements to be formed gradually. This process is responsible for the creation of elements such as lead, strontium, and barium. 7. Supernova nucleosynthesis and the R process. Supernovae, particularly those resulting from the explosion of massive stars, are intense environments where the R process occurs. During a supernova explosion, the energy released is so colossal that it causes the atomic nuclei to rapidly capture neutrons, leading to the formation of heavy elements. The extreme conditions of a supernova, such as high temperatures and densities, provide the ideal environment for the R process to take place. As the neutrons are rapidly captured, elements of increasing atomic number and mass are synthesized, resulting in the abundance of heavy elements we observe in the universe today. 8. The R process and stellar mixing. In addition to supernovae, other astrophysical events contribute to the distribution of R process elements throughout the universe. One mechanism is stellar mixing, where material from a supernova explosion is incorporated into the interstellar medium and can later mix with other clouds of gas and dust. This process allows the R process elements to be dispersed across vast regions of space, increasing their likelihood of becoming part of new stars and planetary systems. 9. The role of neutron star mergers. Neutron star mergers represent another important source of R process elements. When two neutron stars orbit each other in a binary system, they may eventually spiral together due to gravitational waves, resulting in a merger. This event releases an enormous amount of energy in the form of gravitational waves, gamma-ray bursts, and an ejection of neutron-rich material.